In this video, what we're going to look at is we're going to start to introduce the topic of sequences and series. Now, this is a very important topic to study at higher, as it comes up very frequently in the exam and in a lot of the material that we look at throughout the course. Now, what we're going to look at in this video is defining what a sequence and a series is, taking them and seeing how we can use them to develop sequences and relationships between numbers, and how we can actually use them in that respect. First thing that we need to understand is what we're talking about when we're saying a sequence or a series. Now, a sequence, we've encountered that in the past. It's an ordered list of objects, usually numbers. That's what we deal with in maths, is numbers, so that's what they tend to be. You can have different sequences. So we've done bits in the past where it's been maybe a sequence of letters and you have to decide what it represents, or a sequence of images. What do the images represent? What we're going to focus on though is when they're numbers. Now, a key thing that you need to understand is that they follow a set pattern, and it's given by a rule or a formula. So sequences have a rule that they have to follow, which tells you what each term means. You'll notice a pattern between them, you'll notice how it works, and you can calculate any term within the sequence. And there's a type of notation that comes into play when we start to look at sequences and series at higher. And that's labelling everything using subscript numbers. So that's when you've got the main part, U, which represents our term, and the 1 at the bottom tells you what term it is. So this U1 tells me it's the first term. U2 tells me it's the second term, not the Irish band. U3 tells me it's the third term. U4 tells me the fourth term, and so on. If I had U1000, that would be the 1000th term in my sequence. We label each of them using this sort of thing here. Now that's if we're after a generic term. We can actually also label our rule using that, because we can label a rule using the term UN. And what that tells me is the nth term. So that just tells me any generic term in the sequence. And what I'm able to do is use this as part of my rule definition to say any generic term in the sequence does this. So to calculate it, I do this. So here's a couple of examples of what I mean. Imagine I've got a table here. Now in this table I'm going to tell you a few formula and what this represents in terms of a list of numbers. So here what I'm telling you is that UN equals n. So quite simply the nth term is whatever n is itself. So this means U1 equals 1, U2 equals 2, U3 equals 3, as the list of terms here tells you. This rule here tells me that UN equals 2n. So the nth term in my list is 2 times whatever term number I'm at. So U1 would be 2 times 1, U2 would be 2 times 2, U3 would be 2 times 3, and that'll give me a list of numbers that will look like this. That'll give me the list of even numbers. Another rule, you can start to build up the complexity if you like. UN equals a half n bracket n plus 1. So whatever the nth term is, I take the number, half it, and I multiply it by whatever that number is with 1 added on. So if it was U1, I'd do a half times 1 bracket 1 plus 1. So I'd have a half times 1 times 2, which would give me the first term here of 1. My second term, U2, would be a half times 2 bracket 2 plus 1. So it would be a half times 2 times 3, which would give me my next term here, the 3. We could follow that and get any term within it. I could even use trig functions if I wanted to. So I'm saying here that UN equals cos of bracket n pi by 2. So I'd substitute in here and I could get the values of that out. So you could imagine U1 would be cos of 1 pi over 2, so cos of pi by 2. We know that cos of pi by 2 is the equivalent of cos 90, which is 0. U2, cos of 2 pi by 2, which is cos of pi, so it's the equivalent of cos of 180 degrees, which is negative 1. So I can use it to get my terms and generate it there. Now if we have a formula for a list, we can work out absolutely any term that is asked of us. It's very straightforward and easy. So if I wanted U1000, so the 1000th term, let's say of this sequence here, what I'd say is U1000 equals a half times 1000 bracket 1000 plus 1. And then I'd calculate it from there. So I'd have a half of 1000, that's 500, and I'd times 500 by 1001, which would then give me 500,500 as a final answer. So I'm able to generically and quickly calculate that. So that's just what a sequence is. So a series of numbers that are represented by a formula. But what if we wanted to link the numbers to each other? That's when we have to introduce another important concept we're going to focus on here. That's when we introduce the concept of a recurrence relation. Now it is very similar to a sequence. It uses a rule, but the next number depends on the previous number. So I've got this rule here as an example, where un plus 1 equals un plus 2. So what this tells me is the next term in my sequence, n plus 1, equals un, so the previous term, plus 2. Now a key thing you have to make sure as well you define with a recurrence relation is if I just have the rule, great, where do I start? You have to define what's called u0. And this u0 here, this is your initial term. Alright, that is your initial term. That's your starting point, where you begin your sequence and your recurrence relation from. What we can then do is plug it in and get the other one. So for example, if I wanted to do u1, I know that u1 is equal to u0 plus 2, which is 4 plus 2, which is 6. I could then use that to do u2, which is going to be equal to u1 plus 2, and I've just calculated u1 as being 6, so it'll be 6 plus 2, which is 8. So it depends on the previous term and I have to put those values in. Now the big issue with this one is if I did want to calculate u1000, I would need u999. And to get u999, I'd need u998, and so on. It would be a bit more difficult and a lot more work to calculate a generic term in this case with a recurrence relation. Now when we're working with recurrence relations, we're going to take recurrence relations of a linear form. That means ones that always look like this. So un plus 1 equals aun plus b. So the next term equals something times the previous term plus b, so plus some generic coefficient. Now, something like this has a lot of uses beyond mathematics. So for example, they're quite usefully used in bank accounts and accounting with money, drugs and dosages with medicine. Things like that can all come into play when we're working with recurrence relation. They're a very important topic and a very important concept to be able to get a grasp of when something depends on things over time and how they affect each other each year. So I'm going to look at a couple of examples of what I mean by this. So let's imagine we've got a system where we say a patient is injected with 156 mils of a drug. Every 8 hours, 22% passes out their bloodstream, and a further 245 millilitres is given every 8 hours. First I want to find the recurrence relation to represent this, and then I want to calculate how much is left 24 hours later. So, for the first part, for calculating the recurrence relation, remember the recurrence relation, our generic form is un plus 1 equals a un plus b. Now this a here, the way to think about this is what percentage of un I'm going to have. So what part or what fraction of the previous amount am I going to bring into this calculation and work with? And this one here, this b, is anything additional that we put in. And by that I mean things that we can take off as well. We don't just have to add things into our system, we could take things out of it. We have to bear that in mind and watch that, because if we're taking it out, it's a subtract. If we're adding things in, it's a plus. Well, we have to read the question and see about this. So every 8 hours, 22% passes out his bloodstream. So every 8 hours he's lost 22%, which means that every 8 hours he's got 100%, take away the 22, so he's got 78% left in the system, which means that he's got 0.78 times the previous one left. So I know that my value of A is going to be 0.78. My addition is then, what am I doing to correct this, or what else am I putting back into my system? Well, looking at this one here, a further 245 millilitres is given every 8 hours. So my plus B is going to be plus 245. So from this, I can write my recurrence relation out. I can write un plus 1 equals 0.78 times un plus 245. Now there's a key thing we also said we need with a recurrence relation. We need the initial term. We have to read the question and see where we start. Well, we've started at the beginning with 156 mils in the system. So from that, we know that u0 is equal to 156 mils. We can then use this to answer the questions. So calculate how much is left after 24 hours. Well, we know the system is every 8 hours, and we know that 24 divided by 8 is equal to 3. So what we know is we've got 3 doses to go. So what we want to be able to calculate is u1, u2, and then our final answer, which is going to be u3. So we have to start that. So we start at u0, which we know is 156. We then know that u1 is equal to 0.78 times that 156, so it's times the u0, plus 245, so the extra dosage that the person gets in. Once we've done that, you just fire it straight into a calculator. We end up getting 146.68. We then go on to u2. Now we know u2 is going to be 0.78 u1 plus the 245 millilitres. Well, u1 we know is this amount here. So that's what we plug in. So we get 0.78 times 146.68 plus 245. Fire it into a calculator. You end up getting 139.4104. We're then on to our last term, the one that we want, u3. So it's the same sort of form, except it's going to be 0.78 times u2 plus 245. Doing that, we get 0.78 times our u2 value, which was this one here, times 139.4104. Plug that in your calculator and you get 133.7401. So then, after 24 hours, what we can then say is 24 hours later, we've got 133.74 millilitres left. We have to make sure we interpret it. We have to put it back into context. There's no point in just leaving it as U3 was this. Great, but what does U3 relate to? What does that relate to? What does it mean? What's the point? Well, we know they've got 133.74 millilitres of the drug left in their system. So we can leave it at that. Okay. This is the kind of scenario that we're able to do with these. This is the kind of scenario we can work with, that we can calculate, and we can use recurrence relations to answer. So here's a couple for you to have a ping at. So, first question, the value of an endowment policy increased at the rate of 5% per annum. The initial value is £7,000. First, write down the recurrence relation for the value after n years, and then calculate the value of the policy after 4 years, so fairly similar to the previous one. And then the second one, a recurrence relation is defined by un plus 1 equals 0.6 un plus 4, and I'm telling you the initial term is 7, so u0 is 7. Calculate u3 and then the smallest value for n for which un is bigger than 9.7. And one key thing I'll tell you for that one, and a wee hint I'll give you, just remember you can't have the 5.3 term. You can't have the 5.3 term. It has to be a full number. So if it's 5.3, think what term that might be that minimum value will occur at. Good luck.